Okay, we are on the week 2 of Mathematical Foundation for IE, or we will learn linear algebra in this course. And this week we will continue discuss about system of linear equations and matrix. Okay, so first we will discuss more on linear system and invertible matrix. Okay. Linear system, we have discussed it a little bit in the first week, and for this discussions, we will discuss more on the solutions related to a linear system. So a linear system, as you remember, can have either condition it has no solution, or it has exactly one solution or a unique solution, uh, or it can have infinite many solution, mm, where if you remember from the discussions that we have previously, where we illustrated in a linear system with two unknown variables, like for if it has no solutions, mean that it can be shown as a two linear system which consists of um, two equations, where we have the two line doesn't really well, it parallel to each other, so it has never meet in any points. So second is that when you have exactly one solutions, where you have the line that is cut into exactly one particular point, and the third one where you have like a line that is actually exactly the same line, so it collide into one to another, so it has infinite many solutions. Next, we will discuss a part with special form, matrix with special form, which are diagonal matrix, triangular matrix, and their applications. Well, it all cover, including diagonal, triangular, and symmetric matrix. Okay. And finally, we will discuss more about the applications of linear system, in which it provides several practical perspective. Okay, discuss several real world applications on how linear system can be applied. For example, we will have like network analysis, designing electric circuits, balancing chemical equations, or polynomial interpolations, and several examples. Okay, previously we know that linear system uh, has either no solution, this one, right? No solution. I am also draw it earlier for you, or it has exactly one solution, or has infinitely many solutions. And we are now in a position to see the theorema that or proof that conditions. Okay, in the book it defines as the this theorema, where systems of a linear equation either has 0, 1, or infinitely many solutions. Only those three possibilities. Okay, there are no other possibility. And um, well, this is the proof of it. I don't think we are going to delve in much detail. You can read it if you are curious about it. So, but basically, this type of solutions, okay, um, means what? Means like a unique solution, or a solution which has only one solution. it was where the when if we draw it in a two-dimensional, it reflect that where all lines intersect into only a single point, indicating a single set of value satisfying all the equations. Okay, and for a infinitely many solutions means that it occurs that the equation represent the same line or plane, so it leading to an overlap solution. And no solution, it means that where it do not interact or typical for parallel lines that never meet. Okay, so this is for a linear equation. And determining the number of the solutions, uh, you can use two approach to find the solution involved in linear equations. First, you can do it graphically, means that it involves plotting the equations and observing their points of intersections. Okay, and then you can use another approach. It called algebraic operations. So it involves like techniques like substitution, eliminations, or matrix row reductions, like what you are going to learn later on. Okay, next, we will discuss how to solve linear system. Okay, using matrix inversion. Yeah. You did learn about matrix inversion earlier, how to inverse a matrix. And um, in linear algebra, we can there is a theorem where it mentioned that if A is a matrix and it is invertible, it where we have a matrix A, okay, that is invertible and is a n by n matrix, so it's a square matrix. Okay, for each n multiplied by 1 matrix B, okay, this one, um, we can solve the equations becoming a multiplied by x equal b exactly has one solution, namely, so if you want to find the variable x, it will be equals to a inverse b. So this proof showing that in order to solve a linear equation, so you convert it to its augmented matrix version of it, which consists of A, X, and B, and then in order to find the value of those X, you can use this formula. In this example, specific linear equation system is given. So you can see it here. So this will be the first equation, second equation, third equation. Okay. Uh, we will find the solution of this linear equation system by using the previous theorem that we studied, which is solving the linear equation system by matrix inversion. Uh, the the step including as follow. First, we need to convert the linear equation system into a form in a metric form as written as follow. So you have matrix A multiplied by X, which will be the variable, equals to B. B will be the right hand side. Okay. A will be the coefficients matrix of the equation system. For example, the first row here we have this one, yeah, 1, 2, and then here also 2, 3. This one also 3, and then the next row here will be 2, 2 here, 5, 5 also here, 3. This one also 3, yeah. and then here is 1 1, and this one actually plus 0 x2, so you have 0 here, and x is here. Okay, 8. And then what about x? X will be the number of unknown variables, so you have variable x1, x2, and x3, so you will have x n by a 1 column, yeah, this one, and row, which is 3 row by 1 column, and you will also be a b, which is the right hand side matrix. And then in order to solve this one uh, by inversion, so first you need to calculate the inverse of a inverse for a three-dimensional matrix. You can do using the procedure that I already explained earlier. For example, you can go back to the book and see example number 4, or if you are interested on using the software so-called Symbol Lab, you can click this link. There you will be explained the step-by-step of calculating the inverse of a matrix. Okay, so here we got the inverse, okay, this one, and then using theorema of the previous one that we explained earlier, so we can use this in order to find x, okay, the value of the x here. What is x1, what is x2, what is x3? We can use this formula, x equals a inverse multiplied by b. A inverse, we have it here, okay, and then b, we have it here. Okay, here is the a inverse, this one is b. Okay, for example, the value of x, you can get it by multiplication of this multiplied by this. So it will be equals minus 40 plus, multiplied by 5 plus 16 multiplied by 3 plus 9 multiplied by 17, and you will get this value. And the rest is the same. So to x, for x2 you this multiplied by the this column. For x3 is this one, this row multiplied by this column. Okay. Finally, you will get this value. This will be the value of x, in which we can translate it into x1 equal to 1, x2 equal to minus 2, x3 is equal to 3, 2. So later on, if you input this variable to the original linear equations, for example, here you put 1 plus 2 multiplied by minus 1 plus 3 multiplied by 2 will be equals to 5. Okay. Yeah. So basically, it's uh, the way you solve linear system with matrix inversion. In the next example, we will deal with the on how solving two linear systems at once. So both of which in which both of the linear system has the same square metric coefficients. Let's call it matrix A. Okay. The process involves solving the system efficiently using matrix inversion and Gauss-Jordan eliminations. Well, let's see how does it demonstrates. So first of all, let's take a look of the problem. When we have two different linear system, let's say this one, linear system A and B. However, both of them have the same matrix, coefficient matrix A. You can see here the coefficient matrix A of both systems is equals to 1, 2, 3, 2, 5, 3, 1, 0, 8. And then we are going to find the value of the x. However, we have different right hand side here. Yeah, the value of b, the right hand side is different for both. Okay, and well, if you want to solve the each system, of course you can go back to the previous theorem where you have x will be equals to a inverse multiplied by b. So you just need to find the a inverse once. Yeah, right. And But another way, instead of solving them separately, in the textbook it is demonstrate also a method where it involves forming a partition matrix by augmented the coefficient of matrix A with both B1 and B2. Let's say this one is we have B1 here, this one B1 for the system 1, B2 is for the system 2. And then this augmented matrix, for example this one, you remember augmented matrix, right? This is the coefficient A. However, on the right hand side you have B1, B2. Okay. And then, if you remember from the previous approach, we learned about Gauss-Jordan elimination method, in which you need to like turn this matrix into its identity matrix, like below the make all the diagonal equal 1, and below the diagonal will be all 0, and upper is equal to 0. Okay. You remember to do it, right? How to do it. And then um, okay, for example, for the first row, because it's already the leading one's already here, and then you just need to make this one row 1, row 2, row 3, this one become 0 and this one become 0. Okay, the first one, maybe you need to create the second row. New second row will be equals to the first row minus 2 multiplied by the first row plus the second row. So what you do is that first you will have minus 2, 1 multiplied by minus 2 is minus 2, and then you 2 multiplied by minus 2 is minus 4, 3 multiplied by minus 2 is minus 6, and then 4 multiplied by minus 2 minus 8, 1 multiplied by minus 2 is minus 2. Then you plus 2, 5, 3, 5, 6. Then plus it here, you get 0, 1, minus 3, minus 3, 4. Okay, then you have this second row. And then you do that up until it becomes the finish the forward and backward phase, and then you will get this matrix. Finally, you can translate this will be the solution. This will be x for the first linear equations. This will be solution for the second linear equation. So this one is x1, x2, x3 for the first linear equation. Yeah, this one. And then this one will be x1, x2, x3 for the second linear equation, which is this one. Okay, next is a theory that we have seen earlier, in which it's shown relationship between a square matrix, two square matrix, let's say A and B, and its really relationship with identity matrix and the inverse property of it. Okay, so this theory mentioned that, so let's say if you have a square matrix A, this one, and then also another square matrix B with the same dimension. Uh, if A is a square matrix, and then if B is a square matrix satisfying this condition, B multiplied by A equals identity matrix, then you can certain that B is actually A inverse. The other way around, when A and B is a square matrix, previously we have B multiplied by A, now we have A multiplied by B. It's also defined that B is the inverse of A. Okay. Next is about equivalence statement. Okay, equivalent statement. Okay. What does it mean, equivalent statement? Is is a conditions related to invertibility of a matrix. So means that when you have let's say matrix A, and then A has its inverse. Okay, there is available A inverse. Okay, when you have A inverse, okay, A, it means that A is inversible, then all this following statement is also equivalent, means that is also true. And the other way around, if you have the A is not inversible, so it's not inversible, then all the following statements is also false. Okay, so for example, if A is inversible, then you will have an A multiplied by X equals 0 is the trivial, has only trivial solutions. Okay, and then the reduced row echelon form of A is IN. So there are several there is a reduced row echelon form of this matrix A. And then A is expressible as a product of elementary matrix. Yeah, because it can uh, derive down until its reduced row echelon form, then it is also a product of elementary matrix. And then AX equal B is consistent for every n multiplied by 1 matrix B. And then A multiplied by B has exactly one solution for every n multiplied by 1 of B. Okay, so it means like for each the variables. So let's use this theorem later on in the example. Okay, earlier I mentioned that we will discuss three spatial matrix. One of them is diagonal matrix. So let's start with the definition and example of diagonal matrix. A diagonal matrix is a square matrix, okay? Square matrix that has the same dimension, okay, n by n, for example, where all entry outside the main diagonal are 0. So main diagonal is the entry that has the same number of row and column, okay, index of row and column. For example, entry 1 1, entry 2 2, entry 3 3 until entry n n. All of this has value that are not equals to 0. Okay, take example of this one, a 2 by 2 matrix and this one 2 by 2 matrix. This one is called diagonal matrix, okay, because all the entry is non-zero. Sorry, all the entry of the main diagonal are 0. Okay, so when you have this one, 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 this one is equals 0, then you have the diagonal matrix. But for the diagonal itself, it doesn't matter whether it has value other than 0 or equal to 0. Okay, so that's why this one is also diagonal matrix. So here, and this one all 0, this also 0 0, this one also 0 0 0. So these four are all example of diagonal matrix. Okay, now since we know that inverse of a matrix is a take important role on solving um, linear equations system, what about inverse of a diagonal matrix? Okay. A diagonal matrix is invertible. Okay, it can be inverse if and only if all of its diagonal entry are non-zero. Okay, so when you have the diagonal, one of the diagonal is 0, then you cannot inverse it. But if you have all of its diagonal are non-zero, in this case the inverse is 1. Inverse of 1 is the diagonal, the inverse of it. For example, you have this one. Okay. So you have the value up here. This matrix, all this, the value of D is not equal to 0. Yeah, D1 is not equal to 0. D2 also not equal to 0 until Dn is not equal to 0. Then the inverse of it, of this matrix, this D matrix, is the same matrix, but the value of its main diagonal will be 1 per the entry of the previous one, di. Yeah. So it is confirmed the formula by, you can show that when you have this one, multiply this with this, okay, this with this, then you will have this value, identity matrix, where it is 1 0 and then there's 0 1 until 0 0 until C1, like this, okay, identity matrix. And then we can talk also power of diagonal matrix are easy to compute because we can, whenever you have k matrix D, for example, the one that we used earlier, to the power of k, you just need to be calculate the power of the diagonal by to the power of k of it. Okay. So for example, this one, yeah, all the value is has value other than 0, so it's inversible. So the inverse of this D matrix, the inverse is equal to 1 per 2 0 0 minus 1 per 5. What about D to the power of 2? Then you can have 2 to the power of 2, 0 0, and minus 5 to the power of 2. Okay, so that's how do you use this. Okay, one special property of diagonal matrix is that it is also easy to conduct the products of a diagonal matrix to another matrix. For example, here we have a diagonal matrix D, and then we have um, a matrix A, let's say it like that. A diagonal matrix D is a 3 by 3 matrix, and then A here is a 3 by 4 matrix. Okay, so when you have a 3 by 3 matrix, so this one is a D multiplied by A, 3 by 3 matrix multiplied by a 3 by 4 matrix, so you will have new 3 by 4 matrix. So you see that the pattern of DA here is that you see that each of the column will have, each of the row will have the first value of the D here, and second one will all have D2, and then the third one all have D3. So the rest of it you just need to multiply it with the original entry here. So you don't really have to calculate it using the previous formula when you have row multiplied by columns, but you can do it manually like that, but the result will be the same. Next, what if you change the sequence A multiplied by D? It still have the same, the similar pattern, but instead of moving along the row, now you have along the column. See? Column 1 all have D1, column 2 all have D2, column 3 all have D3. and then the rest of the entry is the same. Yep. Next we talk about another special matrix called triangular matrix. A square matrix, okay, in which all of the entry above the main diagonal are zero are called lower triangular. Okay, so now you have the diagonal here. When you have this one, when you have all the entry in the main diagonals above the main diagonal, so this one above this main diagonal, all is equal 0 like this one. Okay, this is what you call a lower triangular matrix. Okay, the other way around, when you have all entry below the main diagonals are 0, so this one below of the main diagonal, we call this one an upper triangular matrix. Okay, this is more precise definitions about triangular matrix. You can read about it. Okay, now let's talk about what uniques from the property of triangular matrix. Number one, it's transpose. So the transpose of a lower triangular matrix is actually an upper triangular. So, and vice versa. Uh, And then about the matrix multiplications. The product of a lower triangular matrix is a lower triangular matrix again. And the product of upper triangular matrix is also an upper triangular matrix. Okay. Another one is invertibility of it. A triangular matrix, so it is either upper or lower triangular matrix, is invertible if and only if its diagonal entry are all non-zero. Okay, remember the value of their main diagonal, all of this is non-zero, then it can be inverted. So more about the inverse of triangular matrix. The inverse of an invertible lower triangular matrix is also lower triangular, and the inverse of invertible upper triangular matrix is also upper triangular matrix. Okay. Okay, in this slide, include example and demonstrations of the property that we discussed earlier. For example, here we have a matrix A, um, an upper triangular matrix where it is invertible, since we know that the upper triangular matrix, and we know that all the diagonal value has value non-zero. Meanwhile, B, it's also upper triangular matrix, but the value, this is non-invertible since one of the diagonal has a zero value. Therefore, we can prove that okay, we can inverse A, then we can have this one. And then if we calculate A or multiplied by B multiplied by A, the result will be both upper triangular matrix. We will try to calculate it later in the class. Next, we discuss about symmetric matrix, where a symmetric matrix is a matrix that has that is equals to its transform. So when you transform a symmetric matrix, so it doesn't change anything, still the same value. Okay, it is easy to recognize a symmetric matrix by just inspections. The entry on the main diagonal will have no restrictions, so it can be any value. So this one, it can be any value, but you can see mirror image of entries across the main diagonal must be equal. For example, here you will have 4, here you will have 4. For this one, the main diagonal, we have this one will have 5, you will have 5. This one you have 0, this one you have 0. Okay, this when you transpose this one, so the row become the column. Okay, so you have 1 4 5 here, and then 4 minus 3 0, and then 5 0 7. So when you transpose it, the value of the transpose is exactly equals with the original matrix, so it's called the symmetric matrix. Next, we talk several more property of symmetric matrix. The first that we already discussed earlier, which when you transpose a symmetric matrix, the result is equal to itself. So for example, this one, if you transpose this, become the column 7 minus 3, and then this become the column minus 3 5. So you see that both matrix is equal. Now you can try to do exercise to transposing these two matrices. Okay. And in another notes, you can follow this formula, this one, to show that a square matrix A is a symmetric if and only if the value of the index Aij, the entry Aij will be equals to Aji for all the entries. Okay, so this one symmetricity, when it's, yeah, this one, A and B are symmetrics, and if K and is scalar, then A transpose is a symmetric matrix. A plus B equal, and B, A minus B are symmetrics. Okay, and then K multiplied by A, so if you have a scalar multiplied by a matrix, the result will be still a symmetric matrix. Okay. Okay, earlier we talked about the symmetric matrix and inverse. Now we explore more about the product of symmetric matrix in an example. Uh, the first of the following equations show that a product of symmetric matrix is not symmetric. Okay, this one. Okay, and the second show that the product of a symmetric matrix is symmetric. For this one, can you see why? Okay, it is because of something that we will discuss in this theorem. Let's say A is an invertible symmetric matrix, then A inverse is also symmetric. Um, Later on, you can prove that when A is a symmetric and is inversible, so when you have the transpose of those symmetric and inversible will be equals to transpose it first and then inverse it later. It will be still equals to the A inverse. And then this will prove that A inverse is a symmetric. Next, this slide uh, show an example that illustrate the symmetry of matrix and their algebraic property. For example, the one we just learned, transpose. Uh, so when you have a product of A between A and its transpose, and we will show also A transpose multiplied by matrix A. So if you, so this is the property that you can have, like this one is equal to this one and this one, and this one equal to this one equal to this one. So you use the most simplest one, have this one and this one to calculate it. And another one, we will show that a product of a matrix and its transpose is a symmetric matrix. Okay, so when you multiply this matrix multiplied with its transpose, so let's say this is matrix A, so when you transpose it, so it's become a 1 minus 2 and 4 and 3 0 and minus 5. Okay, yeah, this one. This one, yeah, the transpose A transpose multiplied by A. Then you can see here this matrix is a symmetric matrix. You see, minus 2, minus 2, minus 11, minus 11, minus 8, minus 8, right? Enough about the fundamental theory about matrix. Now let's see how does this linear equation systems um, take actions in a real case problem. For example, here, this is one of the simple applications about how we can use a linear equation systems to represent networks, and we can conduct some like basic network analysis by using a linear system. So figure 181, which is this one, shows networks where we have um, networks that consists of 4 nodes. Let's say, I don't know, maybe next slide will have the notations, but let's try. Let's say this one is node A, node B, node C, node D, let's say like that. And then from node A, there is a flow. Let's say this is a network, like you have nodes, this one called nodes, okay, and each this one, the connecting one node to another one, or coming in and coming out to nodes, we can say it's an edge, okay. Network analysis problems is having a lot of applications, including like computer networks, or real road networks, for example, or in IE we can often also discuss about logistics networks. So this type of illustrations perhaps can be used as a simple application of those particular problems. So let's say you have here, uh, uh, you know that there are at least 30 uh, 30, let's say, products maybe, or if it is computer network, maybe data package coming into this nodes A, and then it branch out to these two nodes. It becomes, let's say, this one x1, x2, okay. From 30, some of it go to this one, some of it go to this one, let's say x2. And then out from B, okay, it's 35, out from D is 55, okay. And then from node C, we know that there are 60 package going into the C, and then 15 we know that going out here, and then here, let's say x1, x2, x3, some of it out from this one, okay. Now the question is, how do you know what is the value of x1, x2, x3, right? In order to know the network flow of it, okay. This one, okay, this one we can interpret it as a network application of linear systems, especially in linear networks analysis. You see that, oh, I guess it correctly. So here will be A, and this will be B, C, D, and then this one x1, x2, x3. Okay, so you know that when you want to know how many goes to nodes A, okay, the one that goes to node A, of course, this one will be the total of x1 plus x2, which would be equals to 30, because what is coming in is equal to what is coming out, right? And then what is going into node B, yeah, this one, so it's actually equals to x2 plus x3, and it equals to 35, right? And then you go to conduct it again. So for node C, okay, 60 will be equals to 15 plus x3. Yeah, okay. And then node D is x1 plus 15. yeah, equals to 55. And then you put all these equations, so you have four equations where you know that x1 already is here, is 40. Okay, and then you can replace it back. So x1 is 40. Okay, then you put the value of x1 here, you got x2, and then you put the x2 here, you got x3, and then you get finally s, you already have x3 here, 45. Okay, so basically this is one of the applications of a linear system, in which for this one it is easy enough to be represented and then to be calculated easily, so that you can like understood it, the application of it. And sorry, okay, now let's see the fact that the result of this one, you can see it here. uh, if you just substitute it that way, the solution will be x1 is 40, x2 is minus 10, and x3 is 45. Now, what does x2 is equals negative means? It tells us the directions, this one, x2 here, assigned to that flow is incorrect. That is, the flow that the branch is actually some of it going here, something like that. Okay. Okay, next we still talk about network analysis, in which this one may have more detailed case study. Uh, let's read about it. So later on, you will see figure 182, which show a proposed plan for a traffic flow around a new park that will house the Liberty Bell in Philadelphia, Pennsylvania. Okay, so you deal about how to deal with a net traffic flow or network flow in those particular area. The plan called for a computerized traffic light at the north exit on the 5th Street. Okay, later we will see which one is it. And the diagram indicates that the average number of vehicles per hour that are expected to flow in and out of the street that on that border are that border the complex. All the streets are in one way, so this one make it is easier. Now the question is, how many vehicles per hour should be traffic light led through to ensure that the average number of vehicles per hour flowing into the complex is the same with the number of vehicles flowing out. So you want vehicle go in here and then go out, the flow is equal to make it doesn't have bottleneck. Assuming that the traffic light has been set to balance the total flow in and out of the complex, what can you say about average number of vehicles per hour that will flow along the street that border the complex? So you have this one, let's say a square like this. I don't know, maybe like this, like this, right? Some come up here, some going in here, some out here, some going in here. So how do you manage the flow over here, over this complex? This one illustrate the uh, figures so that you can understood it better. So we have this one, right? Okay, this is the orientation. So north is up there. Traffic light is here, and then you can see that it is on the 5th Street. So this one inflow to the park. This also inflow to the park, and then let's go through, pass through here. This become the outflow here, pass to the park, and then this one another inflow out here, and then another in here, and then out here. Okay. So now you can translate this into a more general descriptions, like similar with what we have earlier. So let's say this is node A, node A, node B, node C, node D. Okay, you can see that we want to find this 1, 2, 3, 4 variable. However, we don't have the total of value of outflow in from node B here. So uh, let's say we put a variable called x here as the number of the vehicle per hour that the traffic light must let through. Okay, um, and then they wanted the flowing in is equal to the flowing out. Okay, we know that the one that flow in is the one that has this arrow. Okay, and this one, so you have like 500 here, and then 400 here, and then 600 this one, and 200. Yeah, then equal 1700. The flowing out one, this one 700, and then this one 400. So plus the last one, this one x here. Okay, so when you have like the flowing in equals to out, means that you will have the value of x is equal 600, because this one is x plus 700 plus 400 equal sorry, this one is out equals to in, so this one is equal to 1700, then you will have the x is equal to 600. Now if we discuss about how to manage the congestion inside of those border in the park, so you need to find the value of this one, x1 2 3 4, x1 2 3 4, right? So the number of flowing in and flowing out in node A, okay, we can derive it one by one by its nodes. So for example, here in node A, in is this one, out is this one, right? So in is 400 plus 600, out is x1 plus x2, and then uh, for node B, in is this one, this, and this one, out is this and this one, and we know this is 600. So x2 plus x3 equal 400 plus x, or 600 earlier. So C will be equal in this one plus out, equals to out, this and this one. So in is 200, 500, yeah, and out is x3, x4. D is x1, this one in x1 here, and x4 here is equal to 700. Okay, then you have the linear equations, and then you can solve it using substitutions that we have earlier, or you can use several methods that we already studied. Okay, then what we have here is that if we put back x is equal 600, where we calculated earlier, so then we will have x1 plus x2 equal 100 for equation 1, x2 plus x3 equal 100 for equation 2, equation 3, and equation 4. Okay, and then later on, please try to calculate this. You will find out that x1 will be equals to 700 minus one particular value is t, and then x2 is 300 plus this is an arbitrary value, x3 is 700 minus 3, and x4 is equal to some value. Okay, and it's a parametric t. However, here t is not a completely arbitrary, because there are a physical constraint to be considered on the flow rate of this t, because t, you can see here that it should be between 0 to 700, because this value, right, from 0 to 700, which imply that x1 will be from 0 to 700, x2 will be from 300 to 1000, x3 will be from 0 to 1700, and this one as well. The last one, I will not discuss it in the video. I will give the opportunity for you to see this example and then go to the book, read about it and about the explanation as well. Later on, I will ask someone in the class to explain about it. Okay. Okay, I think that about the last example. The result of the last example is shown here. It is also a parametric result. However, again, the t is not arbitrary, because it should be the smallest positive integer to balance the equations. Yes, that's about it. Please try to study about this last example and we will discuss it in the class.